noise or any other distractions like that. So if you've got a question during the class this evening, just type it into chat or hit the little question thing to raise your hand. And we'll go ahead and get started here with our advanced spotter class. Again, my name is Sam Schamberger. I'm one of the lead forecasters here at the National Weather Service in Nashville. And this advanced spotter class is going to cover more advanced topics than we usually do in a spotter class, get a little more in depth and cover some more stuff that we meteorologists use at the National Weather Service. So a little more in-depth stuff to help you maybe understand some of the meteorology a little better. All right, so we're going to talk about quite a few things here. The class should last about an hour and a half roughly, and we'll take a break about halfway through, so a little bathroom break there. But we're going to cover some topics such as thunderstorm ingredients and thunderstorm parameters. We're going to skip the reading and sounding part for time, and then talk about radar products and signatures, the SPC and some of the products that they use, and then we're going to go through a case study together and kind of combine everything together into an actual event that happened. All right, so we'll go ahead and get started here. Give me 1 second. Make sure everything's working here. All right, so we'll go ahead and get started here. Okay, so first of all, what does it take to make a thunderstorm? Well, there's basically 3 ingredients that you need to form a thunderstorm. You need instability, which is basically air rising vertically in the atmosphere. You need a moisture source, which is basically the fuel or the gas for a thunderstorm to form and build. And you need a source of lift, some sort of mechanism that'll lift the air through the atmosphere, something like a front or the heating of the day or something like that. And to make a severe thunderstorm, you also need something called wind shear. And this is basically the change in wind speed and or direction with height. And we'll go into that more in a little bit. But instability is one of the main ingredients for thunderstorms. And you can think of that as being similar to when you boil a pot of water on the stove. You know, when the water starts to heat up, that you start to see that steam rise off of the bubbles. And that's basically the instability from the heat in the pot rising up through the atmosphere. And it's kind of the same way you can think about like in the summertime when it's hot and those clouds start to build in the afternoon and then they develop into pop-up thunderstorms during the summertime. It's kind of the same way when you're dealing with instability. And so basically, if you've got a bubble of air at the surface, it rises through the atmosphere. It's what's called the dry adiabatic lapse rate, which is about 5.5 degrees Fahrenheit per 1,000 feet. And once the parcel of air rises up and reaches what's called the dew point, that's when the clouds start to form. The water condenses, a cloud starts to form, and that releases energy. And that's how a thunderstorm can get started. Especially if that air parcel starts to, once it condenses, starts to accelerate through the atmosphere. And that's, once the air parcel is condensed, saturated, it starts to rise at what's called the moist adiabatic lapse rate. And that's basically about 2.7 degrees Fahrenheit per 1,000 feet. So basically, for moisture, you just need to be able to lift that air parcel and it's got to condense and then keep rising through the atmosphere. And I also mentioned lifting mechanism. Basically, you need some sort of way to lift that air through the atmosphere. You either need a front or a heating of the day or some sort of upper level jet streak or something like that to be able to lift the air through the atmosphere. And for instance, the animation that's going to show on your page, this is what happens when an upper level disturbance, or what we call jet streams or jet streaks, move across an area. That causes the air beneath it to rise through the atmosphere, and that can be a source of lift for thunderstorms. And of course, you all know cold fronts and warm fronts also lift air through the atmosphere, and that lift from those fronts can help develop thunderstorms as well. And in fact, here's a diagram of a warm front at the top and a cold front at the bottom. And we'll look at the cold front first. That's at the bottom. And a cold front is basically a wedge of cold air moving across the landscape. So when that wedge of cold air, which is denser than warm air, hits an area of warmer air, that warm air is lifted up and over the colder, denser air at the surface. So you can kind of think of that like when you get out of the shower, you've taken a hot shower, and you open the bathroom door and you feel all that cold air rush in at your feet. That's kind of like how a cold front works. Because the cold air is more dense than the warm hot air in the bathroom, it rushes in beneath it. And that's how a cold front kind of works. And a warm front is kind of the opposite of that. It's warmer air being lifted up and over colder air at the surface. So they kind of work in opposite ways. And again, with the warm front, the warm air is less dense than the cold air, so it'll go up and over the cooler air at the surface. All right, and I mentioned wind shear. This is an ingredient you need mainly for severe thunderstorms. You don't have to have it for regular thunderstorms, but it's a requirement for severe thunderstorms. And basically wind shear, there's different kinds of wind shear, but there can be wind shear that's a change in wind speed with height. There's also wind shear that's a change in wind direction with height. And then there's wind shear that's both. It's a change in both speed and direction with height. So if you're looking at number one here on the left, at the surface, let's say we've got a west wind blowing at 5 miles per hour. But as you go up in the atmosphere, let's say you go up about 10,000 feet, well, that west wind's blowing at 30 miles an hour. And then if you go up to 20,000 feet, that west wind's blowing at 50 miles an hour. Well, that's a change in speed with height. So that's a type of wind shear. Now let's look at example number two. This is wind shear that's direction changing with height. So at the surface, we've got a southeast wind, and then you go up about 10,000 feet, we've got a due south wind. And then you go up another 10,000 feet, we've got a southwest wind. So the wind direction is changing with height. And if you combine those two together, you've got the wind shear, the wind is changing to both direction and speed with height. So at the surface, we've got let's say a southeast wind about 10 miles per hour, but you go up about 10,000 feet and you've got a south wind about, let's say 30 miles an hour, and then you go up another 10,000 feet and you've got a southwest wind at 50 miles per hour. You've got not only the wind speed and direction changing with height, but that's going to allow air parcels to try to rotate in the atmosphere. And that's how we can get severe thunderstorms to develop. All right, so I've got a couple questions here. So the cap, the question is, so is the cap heat that prevents heat from rising further up? Yes. If you've ever heard that term cap in the atmosphere, that's basically a layer of warmer or drier air that's preventing the air parcels at the surface from rising up through the atmosphere and creating thunderstorms. But if you get enough instability, or the source of lift is strong enough, it can actually rise up and through that cap, or force the air to go through that cap and create thunderstorms. And another question is, where do these winds come from in the atmosphere? All the wind shear and the winds at the surface are created from different pressure systems across not only the country, but the world. So low pressure and high pressure, the difference between the two will create different pressure gradients, which result in the wind that we experience across the country. So I hope that answers that question. And I did see somebody say they're not hearing any sound. If you're not hearing any sound, make sure you've got your speakers hooked up correctly and turned up all the way, and the sound should be coming through your speakers. All right, so wind shear, again, that's the wind direction and wind speed difference with height. If you've got weak wind shear, that means there's not much either directional or speed change with height. And that's not going to do much with thunderstorms. They're basically going to build up and come straight down where they are. And if the storm builds up and dives right where it is, it's going to choke itself off and probably be short-lived. But when you have stronger wind shear, that allows the updraft of the thunderstorm and the downdraft to be separated. And so the thunderstorm can kind of cycle for longer periods of time and last for a longer amount of time. And therefore, that's why when you have stronger wind shear, we can get those severe thunderstorms, because they last for longer periods of time. So taking all that into account, we're going to go into some more thunderstorm parameters. All right, so one of the ways we measure instability in the atmosphere at the National Weather Service is by using CAPE. And you've probably heard of this before, but CAPE stands for Convective Available Potential Energy. And it's basically the amount of energy in the atmosphere that's available for thunderstorms to form. And the higher amount of CAPE that you have, the stronger the thunderstorms could potentially be. And typically higher amounts of CAPE are correlated with increased amounts of severe weather potential. And basically, to get higher CAPE, you need warmer, more humid air at the ground and colder, drier air aloft. And when you've got cold air above warm air, remember that warm air is going to want to rise, and it's going to, especially if it's colder aloft, that warm air is going to accelerate through the atmosphere. And if you've got higher amounts of CAPE, you're going to see more intense thunderstorms. So what kind of values are we talking about here? Well, basically anywhere from 100 to about 1,000 is considered small CAPE. Basically, you're not going to get super intense thunderstorms just with that amount of CAPE alone. But once you start getting above 1,000, 1,000 to 2,000, that's considered moderate amounts of CAPE. And really anything over 2,000 is considered large amounts of CAPE. And a lot of times in the late spring, especially in the plain states, you can see CAPE values of 4,000, 5,000, or even 6,000 out there in like Oklahoma, Texas, Kansas. And that's an extreme amount of CAPE. So basically it's like, it's not going to take a whole lot to create a very intense thunderstorm. And the more amount of CAPE you have, the stronger the updraft in the thunderstorm. And the updraft can rise at over 100 miles an hour when you've got really intense amounts of CAPE. All right, so we're going to skip that poll question there. And the kind of opposite of CAPE is convective inhibition, or CIN, C-I-N. And this is basically a measure of the strength of the cap in the atmosphere or the downward motion in the atmosphere. And a lot of times there can be that cap in place that's not allowing thunderstorms to form. But if you've got that cap and you've also got intense instability in place, that can allow it's like putting a lid on the pot. It can allow that instability to build up, or that energy to build up. And then when you take the lid off the pot, everything kind of just explodes upward. So that can actually be a little bit of convective inhibition can actually be favorable for even more intense thunderstorms in some cases. But at the same time, if you've got too much convective inhibition, that can keep thunderstorms from forming at all. So that's one of the big challenges we have in the Weather Service, is determining if there's too much CIN or not enough CIN for severe thunderstorms to develop. So now let's go into wind shear. So I've got up on the screen here the 0 to 6 kilometer bulk shear, and we use kind of metric measurements in the Weather Service. So one of the types of wind shear measurements that we use is 0 to 6 kilometer shear, and that's basically from the surface up to about 30,000 feet or so. And basically it's combining both the direction and the speed difference from the surface all the way up to 30,000 feet. So if you've got a large amount of shear in that from the surface up to about 30,000 feet, you're going to have a higher number of bulk shear. And typically you want around 35 to 40 knots for supercells to form. And if you've got more than that, then you've got plenty enough wind shear in the atmosphere for supercells or severe thunderstorms as well. Let me skip ahead here. And one of the ways we measure that bulk shear is also what we call storm relative helicity. And this is basically a measure of the potential for thunderstorms to rotate. And if you, just like with shear, a higher amount of SRH, storm relative helicity, means you've got a higher likelihood of severe thunderstorms. And typically we use two different types of SRH. We use the 0 to 1 kilometer SRH and the 0 to 3 kilometer SRH. And 0 to 1 kilometers is about surface to about 3,000 feet or so, and then 0 to 3 kilometer SRH is from the surface to about 10,000 feet. And the 0 to 1 kilometer SRH is really what we look at for tornado potential. And if you've got really high amounts of shear in the lowest levels of the atmosphere, that's really favorable for tornado formation. And if you've got a high amount of CAPE and a high amount of SRH, that's bad news, because that means you could have some really nasty severe thunderstorms out there. And we had both of those, high amounts of CAPE and high amounts of shear, this past Monday across southern Middle Tennessee and into Alabama and Georgia. And that's why we had so many tornadoes down there in Alabama and Northwest Georgia this past Monday. And again, one of the challenges we have in the Weather Service is trying to determine, is there enough instability in the atmosphere? Is there not enough instability? Is there too much wind shear? Is there not enough wind shear? And the atmosphere likes to be in balance. So to get the most severe thunderstorms, you need the right amount of instability and the right amount of wind shear. If there's too much instability and not enough wind shear, you might not get severe thunderstorms. Or if there's too much wind shear and not enough instability, the wind shear can rip any storms that try to form apart. So there kind of has to be a balance in there of the right amount of wind shear and the right amount of instability for severe thunderstorms. And that's one of the biggest challenges we have to deal with when we're forecasting. All right, so let's kind of take all this into account and look at some different kind of frontal systems here. So if, let's say there was a low pressure, an area of low pressure centered over Western Kentucky, and we had a warm front kind of east to west along the Tennessee-Kentucky border there, like on the screen. Typically, warm fronts have a distinct wind shift from the south to the north when you cross that front. And typically we have south or southeast winds to the south of a warm front, but when you go to the north side of that warm front, you've got east winds. And so it's warmer and more humid to the south of the warm front and cooler to the north of the warm front. And so all the unstable, the higher CAPE in the atmosphere is to the south of that warm front. And right along that warm front, though, where you've got the southeast winds switching to a more east wind, that can be an area of pretty high wind shear right along that warm front. So we like to look for potential severe thunderstorms right along where warm front zones are. And that's kind of like what we saw this past Monday. We had a warm front zone pretty close to the Alabama-Tennessee border down into Northwest Georgia. And that's where all those severe thunderstorms and tornadoes kind of developed on right along that warm frontal zone. All right, and so if I go ahead here, again, right south of that warm front's where typically the highest instability and the highest wind shear is available. If you go further south from the warm front, there might be high instability, but the wind shear is going to be a lot less. So the threat for severe thunderstorms decreases the further away you get from that warm front. And of course, if you go north of the warm front, you're in a cooler air mass, so there's not going to be much instability, even though there might be quite a bit of wind shear. So hopefully that all makes sense. And now let's switch gears and look at a cold front. So we've still got the area of low pressure in western Kentucky. And let's say we had a cold front kind of southward from that low pressure down to along the Mississippi-Alabama border. Now, cold fronts have typically a very sharp wind shift. You've got south winds to the east of that warm front, cold front. But then when you go to the west side of the cold front, typically the winds switch to northwest or north. So you've got quite a wind switch there when a cold front comes through. So can be quite high instability, quite high wind shear right there along that cold front. And you've got that warm, humid air mass to the east of the cold front. So that's where you've got high instability and high wind shear. But when you go to the west side of that cold front, the cooler air is coming in and the wind shear is decreasing. So the most favorable area for severe thunderstorms is going to be along and ahead of that cold front to the east side, and drops off significantly when you move to the west side. All right, so let's kind of take all that into account. And this is going to be a question for all of you, so just type this into chat. So looking at this map on the screen, where do you think the best area or the most likely area for severe thunderstorms to develop would be? So is it A, B, C, or D? So just type that in chat and what you all think. All right. Looks like everybody got it, almost got it. Yeah, it's choice A, because at choice A, you're right south of that warm front, and you're also just east of that cold front. So that's where the highest instability is located. That's where the highest wind shear is located. At point C, you're starting to get too far away from that warm frontal zone, even though you are ahead of the cold front. So it's less likely you would see severe weather at point C versus point A. And then, of course, at point B, you're north of the warm front, you're in the cold air, so that's not a favorable area for severe storms. And at point D, you're behind the cold front in the cooler air, so that's not a favorable area for severe storms as well. So, all right, everybody did great. So let's go ahead and move on, switch topics and talk about radar. And I'll pause right here. If anybody has a question, you can type that into chat right now. All right, I'm not seeing any, so we'll go ahead and keep going here. All right, so the National Weather Service has a network of radars all across the country, and these radars transmit a horizontal and a vertical pulse of energy that goes out from the radar dome into the atmosphere. And when it hits something like a thunderstorm or rain or snow or whatever it is, that energy bounces off that particle and goes back to the radar site. And then the radar can measure what it interacted with. So that's how we see rain or snow or any precipitation on the radar, is just that energy going out into the atmosphere and coming back to the radar. And if you've got heavier rain, the radar can determine that from the energy bouncing off the source. One of the issues with the radar, though, is because of the curvature of the Earth, the further and further away you get from the radar site, you have several issues. First of all, the resolution gets poorer the farther away you get from the radar site. So with the radar here in Nashville, we can see the Nashville metro area really well on the radar. But once we're moving out into the farthest areas of Middle Tennessee, like down towards Lawrenceburg or maybe over towards Dover or down towards Winchester, that's pretty far away from the radar. So the radar beam is getting higher and higher above the surface of the Earth. And that's, again, because the Earth is curved. So if we're looking at storm A there on the screen, let's say that's right over Nashville, we can see that storm really well. But if we're looking at storm B, let's say it's over Lawrenceburg, we're looking at the middle to the upper parts of that storm. So we could be missing some of the severe weather that's going on at the surface of storm B because it's just so far away from the radar. So that's one of the issues with our radars. Another issue is that the radar scans can take several minutes to complete, to go through the whole atmosphere. And you guys know that severe weather can occur very quickly. Tornadoes can touch down in just a few seconds. So because that scan takes so long, we can miss some of that severe weather that occurs out there. So even though the radar is an amazing piece of technology, it still has some limitations out there. And that's why we have you guys as our eyes on the ground to spot and see what's going on at the surface. So here in Middle Tennessee, we've got Nashville there in kind of the left center of the screen, and the OHX radar is the main radar for Middle Tennessee. But there's other radars that we use as well. There's the HPX radar, which is Hopkinsville, Kentucky, just across the border from Clarksville. And then we have the HTX radar, which is just east of Huntsville, Alabama. And we use those radars pretty often to kind of focus more on the northwest and southeast parts of Middle Tennessee. And then we also cover the Cumberland, part of the Cumberland Plateau, so like the Crossville and the Jamestown areas, and they're about equidistant between the OHX radar and the MRX radar in Morristown, Tennessee. So we use that radar also to look at storms on the Cumberland Plateau. So there's basically 4 radars that we utilize when we're looking at weather across Middle Tennessee. And there's also, it's not on the map here, but we also use the terminal Doppler radar, which is owned by the FAA, and that's just southeast of Nashville. And we use that also. It covers the Nashville metro area really well. So basically there's 5 radars that we use to look at the weather across Middle Tennessee. So the radar produces several products that we use. The main one that you all are very accustomed to is what's called radar reflectivity. And this is basically the amount of energy returned to the radar once it's hit that source, like I mentioned before. So again, if it's not hitting a whole lot, it's going to measure that as light precipitation. But if it's hitting really heavy stuff, it's going to measure that as intense precipitation. And typically the blue and green colors are lighter precipitation, and the red, orange, and purple and white colors are heavier precipitation. And the other main product that we use with the radar is what's called velocity, or basically it's a measure of the wind speed in the atmosphere or a motion of the targets. And the radar can only measure objects moving towards or away from it. It can't measure things moving at an angle. So it determines if an object is moving towards it or away from the radar using a series of colors. So typically on most radar programs, green is air moving towards the radar and red is air moving away from the radar. And if it's a really intense level of green or a high number wind speed, that means it's very strong inbound towards the radar. An intense red means it's very strong winds moving away from the radar. And if you've got really intense greens right next to very intense reds, that indicates rotation, and that's how we look for potential tornado formation with any thunderstorms out there. And we'll go into all this more here in just a minute. And then we also use what's called storm relative velocity, and that's taking the velocity that I just mentioned and applying the motion of the storm to that. So if the storm is moving, let's say, east at 30 miles per hour, the radar can take what it's seeing with the velocity and then incorporate the storm motion into that. So it's kind of a better way to look at the storm relative winds out there. And you can kind of think of it as like a car driving at 50 miles per hour into a 10 mile per hour headwind. And overall, the car relative velocity would be 60 miles per hour towards the car. And we can use that, and it can show areas of rotation a lot better than just looking at the base velocity product alone. All right. And then we've also got lots of dual polarization radar products. A few years ago, all the National Weather Service radars were upgraded with this dual polarization technology. So now we can also determine the shape of the objects that the energy from the radar is hitting. And so some of these products allow us to see hail, snow, and even tornado debris in the atmosphere. So I'm going to go into all these here. One of the products we use is called differential reflectivity, or ZDR for short. And basically it measures the shape of the object that it's hitting. A ZDR around 0 indicates it's hitting a round object. A ZDR of above 0 indicates it's hitting a horizontal object, and a ZDR below 0 indicates it's hitting a vertical object. So you can kind of think of it, if the radar energy is going out into the atmosphere and it's hitting something that it thinks is around 0, that's probably going to be a hailstone or something like that. And if the ZDR is significantly below 0, it's probably hitting what's likely a spiky hailstone or something that's more vertical in shape. But if it's highly positive and it's hitting something horizontal, that's probably just raindrops, because raindrops, as they fall through the atmosphere, they actually start to flatten out just from the drag of the air in the atmosphere. And I'll go into more of this here in a minute. Let me skip ahead here. And another product we use is called correlation coefficient, or CC for short. And basically this is determining how similar the objects are in a given radar sample. So if all the objects, let's say the radar energy goes out into the atmosphere and it hits a bunch of raindrops, and everything in that area is all raindrops, well then the CC would be 100%, because everything is a raindrop in that area, or a CC of 1. Basically everything is the same. But let's say the radar energy goes out and it hits a mixture of rain and snowflakes. Well, then the CC is going to be lower than 1, because it's got a mixture in there, and it might be in the around 90% or something like that, or a CC of 0.9, because there's a mixture of different objects in there. But once you start getting super low of CC, let's say a CC below 80% or 0.8, you're starting to get things that are definitely not meteorological. It may be detecting bugs or other smoke in the atmosphere, or maybe even tornado debris, because it's just going to be too many different things in the atmosphere for it to be meteorological. So typically meteorological things will have a CC above 80% or 0.8, and everything below that will be probably not meteorological. And got a question here. Are there any plans to add another radar in Middle Tennessee? Oh, do I wish, but unfortunately radars are very expensive. Not only are they expensive to install, they cost over $100 million. They're very expensive to maintain. The electric bill alone is several thousands of dollars a month, and it's just too expensive to install new radars, unfortunately. So hopefully one day we'll get some more radars across the area. All right, so let's look at some radar signatures. You've probably all heard about the hook echo, and basically that is the precipitation in a thunderstorm wrapping around the updraft of the thunderstorm. And it creates that hook shape that we've all heard about on the southwest edge of a thunderstorm. And typically, we want to look at that hook area for potential tornado formation, damaging winds, and also large hail, because the large hail can get wrapped in with that hook area on the southwest side of a thunderstorm. So let's take a look at some radar signatures and kind of combine that with if you were out spotting, what would you see if you were looking at a specific radar signature? So, okay, let me skip ahead here. So let's say we've got this supercell thunderstorm here, like on the screen. We've got that hook echo there. It's kind of between Culver and Minneapolis. It's near that point A on the screen. And let's say you're spotting and you're at point A and you're looking towards point B. Well, what would you see? Well, basically, you'd probably see the top of that thunderstorm there, like at the bottom right of the screen. You could see the overshooting top there on the top of the thunderstorm. That's where the updraft is so intense. It's punching right through the troposphere into the stratosphere. And that's a very good sign of an intense thunderstorm. All right. So now let's look at the velocity signature here. And like I said, greens are signatures indicating wind blowing towards the radar, and red is wind blowing away from the radar. And if we see intense greens next to intense reds, that indicates rotation, and that's where we want to look for potential tornado development. All right, so let's see here. I think my presentation messed up a little bit here, so sorry about that. Let me skip ahead here. Another radar signature that we look at is what's called the bow echo, and this is basically a line of storms, and the line may start to bulge out in some areas, and that's where enhanced or possibly damaging winds are causing that bulge to form in that line of storms. But we can also see sometimes weak tornadoes form in these bow echoes, and we can also see large hail. And like on the image on the right, we've got a line of storms there going from west to east from Russellville towards Huntsville. And you can see some of those bulges within the line. So we'd want to look in those areas for potential strong winds or maybe even rotation in or near those bulges. And if you were out spotting, let me go back to the screen here. Let's say you were in Athens, Alabama. So right about here on the screen, and you were looking south at this line of storms coming towards you, this might be what you see. You'd see this wedge-shaped, pretty ominous looking cloud coming towards you. And that's the shelf cloud on the leading edge of that line of storms. That's where all the winds are gusting out of that thunderstorm line and towards the ground, and it forms that wedge-shaped cloud that we call a shelf cloud. And they can be pretty spectacular visually, but a shelf cloud's kind of the opposite of the wall cloud that we look for potential tornado formation. So be sure if you are looking at a shelf cloud, you're going to want to look for any rotation. You're probably not going to see any because the shelf cloud is gusting out of the thunderstorm. I'll go into more of that here a little bit later. And another radar signature that we look at is called the three-body scatter spike. And this is basically when the energy from the radar goes out and it hits an area of large hail in the atmosphere, and the radar beam gets kind of trapped, bouncing off all those large hailstones in the atmosphere, and it gets scattered out. The energy from the radar gets scattered out in all directions, and it can kind of look like a spike is coming out of a thunderstorm. And basically, if we see that, we know the radar is detecting large hail in that thunderstorm. It doesn't necessarily mean the hail is reaching the ground, but at that elevation of the radar beam, that's where some hail is definitely present. So let's take a look here at an example. So here's the radar in Nashville. It's OHX. And take a look at that storm down by Lawrenceburg, Tennessee. So it's way there at the bottom of the screen. You can kind of see that spike sticking out to the southwest of the storm. That's because the radar beam is going from the OHX site all the way down to that storm by Lawrenceburg, and it's hitting all that area with the purple and the white colors there, and it's interacting with large hail, and it's bouncing the radar beam all around, and it's causing it to spike out to the southwest. So if we saw that on radar, we would know there's definitely large hail aloft in that storm north of Lawrenceburg, and it could be reaching the ground. So we'd want to be looking at that area for possible large hail. And there's an arrow showing that direction that we're looking at from the radar site. And if you look at the dual pole CC product on the radar, this is also a great way to see a hail spike on the radar. So really low CC indicates, especially in that spiky area to the southwest of the storm, indicates that that's not realistic. That's not a meteorological signature. Remember, I said anything below 0.8 is typically not a meteorological thing in the atmosphere. And in fact, you can tell here just to the southwest of Lawrenceburg, all this CC is like in the 50% or lower range, and it's basically a false echo. So the radar it's picking up that three-body scatter spike and determining it's not a real meteorological object. All right, right there on the screen. So I'm going to pause here. Got another question here. Are radar images broadcast over airways, which can be received and displayed on computers? Yeah, basically all the radar images everything's automatic now. Everything goes via satellite or through the internet. So yeah, basically that's how everything is. It's not really like how it was in the 90s. That was a totally different way of how it was transmitted. Everything now is much more advanced. All right. And so we can kind of take all of what we've talked about so far into play and determine this one signature that's called a tornadic debris signature, or a TDS. If we see this on radar, and we've also got a strong area of rotation, area of high reflectivity, low CC, well below 0.8, and the ZDR is negative, all those on top of each other, we can determine that that's actually a tornado that has touched down and has lofted debris into the atmosphere. And we've used this time and time again to confirm tornadoes that are occurring when we've issued a tornado warning. So this has been a great aspect of the dual pole radar upgrade that we got a few years ago. So what does a TDS look like on radar? Well, we've got, you can look at the image on the screen here. This is the El Reno tornado from 2013, just southwest there of El Reno in the white circle. You can see we've got that area of red on the reflectivity at the top left. And then at the same place on the velocity on the top right, we've got a very strong area of rotation. Then at the bottom left, you can see we've got a kind of a ball there of blue CC, which is very low CC, 40, 30% or 0.4, 0.3. And then on the bottom right, we've also got ZDR that's well below zero, probably -1 or -2. All four of those are co-located on top of each other. So we know that has to be tornado debris in the atmosphere. So we can use that, and if, let's say I had issued a tornado warning for the storm and then this signature popped up on the radar scan, I would know that this is a tornado in progress, and I could put that in my warning. So this has been, like I said, a great tool for us to use in the Weather Service. And we can also determine how strong, or estimate how strong a tornado might be based on how high in the atmosphere the debris gets. And so let's say we had this supercell on radar, like on the screen here. We can do a vertical cross section of that storm, like at the top left, and that shows the storm from the surface all the way up to about 50,000 feet in the atmosphere. And you can see the little ball there of low CC on the vertical cross section. And then we've got the blues and greens, the low CC, going all the way up to about 20,000 feet in the atmosphere. And there's even signs it could be going up further than that. If you've got tornado debris lofted miles into the atmosphere, that's a sign that you've got a really strong or possibly violent tornado in progress, or has recently occurred. So that's another way we can estimate how strong a tornado may be off of radar. All right, I'm going to skip that one there. One of the issues though with the radar is, like I said, it can only detect movement towards the radar or away from the radar. So let's say you've got this storm on the screen here that's moving directly towards the radar at 30 miles per hour. Well, the radar is going to see it just fine. It can determine that the storm is moving towards the radar at 30 miles per hour. It's got winds probably moving at 30 miles per hour with the storm. But if that storm is moving at a 45-degree angle from the radar's not going to detect the motion as well and not going to detect the winds as well because it's not moving directly towards or away from the radar. So in this case, if that storm is moving at a 45-degree angle at 30 miles per hour, the radar is only going to determine it as moving at 21 miles per hour, or the winds as only being at 21 miles per hour. So that can give us an erroneous estimate of what the winds may be doing with that storm. So that's one of the factors we have to take into account when we're looking at storms on the radar. And here's another example. Let's say this storm was moving due south at 30 miles per hour, so completely perpendicular to the radar beam. Well, the radar is not going to be able to determine what the wind speed is at all with that storm because it's moving directly perpendicular, not either towards or away from the radar. So that can be a real problem in some cases if we've got a storm, let's say from the Nashville radar, we're looking towards the southwest, and we've got a storm moving directly over downtown Nashville from the northwest to the southeast. Well, that storm would be moving directly perpendicular to the Nashville radar, and we wouldn't be able to determine if there's severe winds going on with that storm in downtown or not, because it's not moving towards or away from the radar. I hope that makes sense. And I'm going to show you an example here that hopefully will make that more clear. So let's say we've got the OHX radar here on the left side of the screen, and we've got this storm east of Nashville near Cookeville, Tennessee. So right here in the center of the screen, here's Cookeville, and we've got this, you can kind of see this hook echo here of this storm just west of Cookeville. The radar beam around Cookeville is about 4,300 feet above the ground. But because this storm is moving almost due south, it's moving perpendicular to the radar beam. So we're not really able to see much in the white circle here as far as the winds are concerned or the velocity is concerned. We're not able to see that very well because it's moving perpendicular. But if we take a look at the Huntsville radar, which is due south of Cookeville, and we're looking at that storm moving right towards the radar, we can see that the velocity really well. And in fact, you can see there just southwest of Cookeville in the white circle, there's really strong greens and really strong reds right next to each other. So there is really intense rotation going on with that storm. And in fact, there was a tornado going on at that time. And that's a photo of the tornado there on the right. So we're not always able to see things from just the Nashville radar, and that's why we have that network of radars, so we're able to see all the different angles of storms and where they're moving. All right, so I know I covered a lot of topics there in a short amount of time, so if you've got any questions, go ahead and type those in now. All right, so we're going to kind of switch gears here and talk about the Storm Prediction Center. And This is a national center that's located in Norman, Oklahoma, and they do a lot of research regarding severe thunderstorms and tornadoes. And they also issue all the tornado watches and the severe thunderstorm watches across the country. So they are in charge of issuing the watches for tornadoes and severe thunderstorms. But the local offices, like my office here in Nashville, we issue the warnings for tornadoes and severe thunderstorms. So that's because the tornado watches and severe thunderstorm watches typically are covering multiple states. So that's why they do that. And then warnings typically just cover a few counties. So that's why we do that. So they've got a lot of great things on their website, though. If you go to www.spc.noaa.gov, you could probably spend weeks going through all the different information and research and tools and storm history and all sorts of stuff on their website. They've got just an unbelievable amount of information on there. So I encourage you to go check it out, just for all the good information on there. But this is also a great way to kind of stay in tune with what's expected as far as severe weather across the country, because they do daily outlooks for the expected areas of severe thunderstorms out 8 days in advance. So they'll highlight areas of the country that they're looking at for potential for severe thunderstorms and refine that as we get closer in time to the actual event. All right, so let me see here. The main thing that the SPC does is they issue these convective outlooks, and that's what I was just talking about with the areas of the country that they're expecting severe weather. And there's different threat levels that they look at, ranging from just plain old regular thunderstorms to marginal risk, which means just a low probability of severe thunderstorms. A slight risk is a little more coverage of severe thunderstorms. Excuse me, an enhanced risk means pretty widespread severe thunderstorms are expected. A moderate risk is very widespread severe thunderstorms are expected. And a high risk means a severe weather outbreak is expected. And the high risks are very rare. There's typically only one or maybe two a year across the country, but the marginals and the slights and the enhanced happen very frequently. So if there's a moderate risk or a high risk of severe weather issued for your area, that's something you should really pay attention to, because that means that they're expecting a major episode of severe weather. And in fact, this past Monday, we had a moderate risk of severe weather across far southern Middle Tennessee into Alabama and Northwest Georgia. So that's where I believe they're up to about 20 tornadoes occurred this past Monday in that moderate risk area. So they don't issue that lightly. That means they're expecting a pretty widespread severe thunderstorm event. All right. So here's some examples of Storm Prediction Center Day 1 outlook. So this would be an outlook they do for today. And so you can see across the country, they've got a very large area that's under the marginal risk, or the green color there on the screen. And then there's a slight risk there in western Kansas. So they're highlighting a bit more coverage there of severe storms. And then there's this big C-shaped arc of an enhanced risk from southern Ohio down into Tennessee and then over towards North Carolina. So that area, they're expecting, or whenever this was, they were expecting more widespread severe thunderstorms in that orange shaded area. And then on the Day 1 outlook, they also highlight areas where they're expecting more coverage of tornadoes, large hail, and damaging winds. So at the top right there, that's where they're expecting tornadoes and their risk areas for tornadoes. So there's a 2% risk in the green area. That's a pretty low risk. And then a 5% risk there in southern Ohio and northern Kentucky. So they were expecting a bit more coverage of tornadoes potentially up in northern Kentucky and Ohio. And then here at the bottom left, that's their damaging wind outlook. So that 30% area, or that red area, that's pretty widespread damaging winds that they're expecting, and that correlates with their enhanced risk there at the top left. And then at the bottom right, that's their large hail threat. So they were expecting pretty significant large hail up in northern Kentucky into southern Ohio and across middle Tennessee in that red area on the screen. So they do all sorts of threat levels and outlooks for severe thunderstorms, not only for today, but out, like I said, 8 days in advance. All right, so I'm going to skip ahead here. Another product that they issue is what's called a Mesoscale Discussion, and this is basically a write-up on the severe thunderstorm threat that they expect here over the next few hours. And it's typically for parts of a few states. And these aren't issued every day. They're only issued for areas that they're expecting either significant severe weather coverage, or there's already a watch in place and they're just doing an update on the severe thunderstorms going on in that watch area. So I encourage you to check these out if there's ever severe thunderstorms going on, because you can learn quite a bit reading these mesoscale discussions and those convective outlooks about severe weather. Another great thing on their website is their meso analysis products. And this is basically a short-term analysis of all the different severe weather and winter weather parameters that we use in the Weather Service all across the country. And you can zoom in to the different sections of the country and see things like CAPE and wind shear and how cold is it in the mid-levels and all sorts of different types of meteorological parameters, and you can overlay them on top of each other, and it really gives you a good idea what areas could see severe thunderstorms, what areas could see tornadoes, what areas could see heavy snow, what areas could see flooding. They've just got pretty much everything there on their website. So again, I encourage you to check that out. And we're going to take kind of everything we learned so far and then let you be the meteorologist here. We're going to go through a case study. But before I do that, I saw there was a few more questions. I'm going to answer those here. Let me see. Is there a website we can go to view all these different images, like monitoring wind direction, CC, and reflectivity? Yeah, our website, weather.gov/Nashville. If you're talking about radar specifically, there's lots of different apps that you can use out there on your phone or programs on your computer. As far as your phone, I recommend Radar Scope. That's a great app. Unfortunately, it costs like $10, but I think it's well worth it because you can just use so many different products and just easily flip from radar to radar across the country. So that's a great app, but there's lots of others as well. And as far as your computer, one radar program we really enjoy is GR2 Analyst or GR Level 3. Those are really great radar programs, but those unfortunately are really expensive. I think they're roughly around $200. So I know that's not realistic for a lot of people, but there's lots of other radar programs out there to use. And Radar Scope even is available now for PC and Mac, I believe. So if you want to try that, it's a lot less expensive than the GR2 and GR Level 3 programs. But those are great programs if you want to use those and learn more about the radar out there. All right, so we're going to kind of take everything we talked about here and then go through a case study and kind of let you be the meteorologist. All right, so let's say this is the weather map across the country, and we're going to focus on Middle Tennessee. So pretend everyone in the class, we all live in Middle Tennessee. All right, so the morning of, let's say this was back on December 23rd, 2015, but let's pretend it's today. So we wake up and we look at the weather map, and this is what we see. Well, there's a pretty strong area of low pressure here in Kansas, and we can see there's this front located across Missouri, Illinois, Indiana. You can see it's got alternating warm front and cold front symbols. That means it's stationary. It's basically not moving either way. So that's what we consider a stationary front. And then there's a cold front extending from that low down into Texas. All right, and we're not going to concern ourselves with the other systems across the country. This low is forecast to move to the northeast towards the Great Lakes. So we'll keep that in mind. Here's the SPC mesoanalysis that morning, showing the Cape and the SIN, or the convective inhibition, across the eastern part of the country. We can see here in Middle Tennessee, there's no Cape present. The Cape is defined by these red lines here, these thick red lines. And you can see down here in the Gulf of Mexico, there's some 3,000s and 4,000s. So there's a lot of instability down here in the Gulf of Mexico. Remember, I said anything over 2,000 is a large amount of Cape. So we're talking 4,000, that's extreme amounts of instability. So there's a lot of warm and humid air down in the Gulf of Mexico. Across Middle Tennessee, these blue hatched lines, that's the convective inhibition according to the SPC mesoanalysis. So right now, the atmosphere over Middle Tennessee, we would consider that stable. There's not any instability, and there's nothing that would suggest severe thunderstorms. All right. So as we move into the middle of the day, here's the SPC mesoanalysis. Looking down here in the Gulf of Mexico, you can see all this instability down here is starting to move to the north. So it's starting to spread across Louisiana, up Mississippi. You can see it nosing up towards Memphis here and up into southern Arkansas. So we've got 1,000 Cape starting to reach up into West Tennessee. And even some of these light red lines are indicating 100 Cape, which is the minimal amount of Cape, starting to nose into Middle Tennessee here. But you can see these blue hatch lines, there's still a lot of SIN, or convective inhibition, in place across Middle Tennessee. So again, there's nothing suggesting severe thunderstorms are imminent across our area. But all this instability to our southwest moving northward is definitely a concern. By 6 p.m. that day, the Cape we can see to the south here, it's moved up into West Tennessee, but it's also spread across almost all of Mississippi, and it's nosing up into Alabama as well. So that big area of Cape is starting to shift towards us here around 6 p.m. But there's still a lot of convective inhibition in place here in Middle Tennessee. So again, not a huge amount of concern for severe thunderstorms at the present time, but with all this instability moving towards us, that is a concern. We could see some severe thunderstorms here a little bit later. So as of right now, what would you rate our severe weather threat here in Middle Tennessee? Is it level 1, no problem? Level 2, might need some coffee. Level 3, could be busy at the office. Level 4, all hands on deck. Or level 5, yikes, we're going to see a tornado outbreak. Just based on what we've looked at so far, type in what you think the threat level would be. This is not, this is kind of a subjective question. Yeah, most of you are getting it. It's really nothing looks like a major threat. It's probably a 1, 2, maybe a 3. There is a concern with all that instability moving towards us. It could get busy later on, but right now there's nothing suggesting there's a major threat, but there is some concern. So probably around a 2 would probably be the best answer, but a 1, 2, or 3 is a good answer. So you all got it. Great job. All right. So now let's look at the wind shear in the atmosphere. So this is the wind shear that morning, the 0 to 1 kilometer SRH, or storm relative helicity. Remember that SRH is a measurement of the amount of rotation potential for thunderstorms. So looking here at 6 a.m., looking here in Middle Tennessee, this is the 200 line up here, and here's the 300 line. So looks like between 200 to 300 SRH is present across Middle Tennessee this morning, which is a little high, but nothing earth-shattering that we're going, oh my gosh, we need to batten down the hatches for. But by that evening, let's look what the 0 to 1 kilometer SRH is showing. So now we've gone from 200 to 300 to way over 500 0 to 1 kilometer SRH across all of Middle Tennessee up into southern Kentucky and northern Alabama. So generally you want to look for around 100 to 200 for potential for severe storms, and we've more than doubled that now. So now we're getting really concerned. That means there's a lot of wind shear present, not only in the atmosphere itself, but in the lowest level of the atmosphere. And that's really conducive for the potential for tornadoes. So, all right, so let's keep that in mind. And now let's look at a deeper layer of the atmosphere. So the 0 to 3 kilometer SRH, again, at 6 a.m., it was like the 0 to 1 kilometer around 2 to 300. Nothing earth-shattering. It is a little on the high side, but nothing major. But by 6 p.m. that day, check this out, over 700 here in parts of northern Alabama up into Middle Tennessee. That's almost triple what we typically look for as far as severe thunderstorm potential, roughly around 250. So we've got over triple that. That's definitely eye-opening. We've got a lot of wind shear in the atmosphere. That's very concerning for severe thunderstorm potential. And here's another product, the 0 to 6 kilometer shear in the atmosphere. So this is the shear from the surface all the way up to about 30,000 feet in the atmosphere, a big layer of wind shear. And we've got, looking here in Middle Tennessee, there's anywhere from 60 up to 80 knots of wind shear. And typically we want to look for around 35 to 40 knots for supercell and severe thunderstorms as far as the 0 to 6 kilometer shear. So we've got almost double that here in parts of Middle Tennessee. So again, a lot of wind shear in the atmosphere, definitely eye-opening and concerning for potential for severe thunderstorms. And I'm gonna skip over that right there. So now, knowing what we know about the wind shear in the atmosphere, and we've also got that area of instability that's moving towards us from the southwest, and it looks like it's all going to come together across Middle Tennessee later this evening. Knowing all that now, what would you all rank the threat level across Middle Tennessee on a scale of 1 being no problem up to 5 being yikes? Yeah, it looks like most of you got it. Anywhere from a 3 to a 5. Since it hasn't all come together yet, we don't know exactly what's going to be happening, but the parameters are so apparently strong and concerning that I would say this is probably a 4, a level 4. We probably need to plan for potential for severe weather. It's not quite to the 5 level yet where we need to take cover, but it's definitely concerning. So 3 or a 4 is probably the best answer for that. So most of you got it. Great job. All right. So what happened that day? So here's the storm prediction day 1 outlook. So this is what they put out the morning of this particular event. So they had put out a moderate risk for severe thunderstorms across western Kentucky, kind of the western half of Middle Tennessee, down into northern Mississippi and eastern Arkansas. And then surrounding that, there's a huge slight risk area from Chicago all the way down to New Orleans. So a big chunk of real estate is covered by at least a slight risk of severe thunderstorms, but there's that moderate risk area in the center of all that. And looking at the top right image, this is their tornado outlook. So they have a 15% area covered there in red of potential tornadoes. So that is pretty close to where that moderate risk area is. And remember I said 2% is low, 5% is more widespread, and 10% would be considered fairly high, and anything over 10% is pretty widespread threat for tornadoes. So now we've got a 15% threat area. That's very high threat for tornadoes. So that's very concerning. And then at the bottom left here, the wind outlook is, if you remember back on a few slides ago, I said 30% was pretty widespread potential for damaging winds, and they've got a 45% area highlighted there in parts of Middle Tennessee up into Kentucky. That's a very high potential for damaging winds. And then the bottom right, the hail is up to about 15% in West Tennessee and up into Illinois. That's not super high. It's about moderate level, medium level. So not a big hail threat, but definitely a big damaging wind and tornado threat here in Middle Tennessee. All right. So at 23Z, so that's about 5 p.m. Now with daylight savings time, it's at 6 p.m. SPC issued a mesoscale discussion, and they said a tornado watch would be issued pretty soon here across Middle Tennessee into northern Alabama. So let's see what they said here. So let's say we pulled up their mesoscale discussion, and they put here in the top of it, probability of watch issuance 95%. Well, that's pretty much as close to 100% as you can get. So they're definitely going to be issuing a tornado watch here soon. And they wrote in their discussion, an upstream broken line of supercells across western Tennessee and northern Mississippi will approach Middle Tennessee and northern Alabama within the next 1 to 2 hours. These storms have recently exhibited an increasing trend in low-level rotation. Modest moistening from the south will continue to occur as the moist axis shifts eastward. This, along with 0 to 1 kilometer SRH values ranging from 300 to 600, recently observed per the area radars, suggests the tornado threat will continue to expand eastward, requiring issuance of a new tornado watch. So what they're seeing is that all that instability and especially that wind shear is going to kind of come together here across Middle Tennessee here pretty soon. So that's why they're going to issue a tornado watch. All right, so here's our tornado watch. They put that out at 4:50 p.m. It goes until 11 p.m. and oops, hit the wrong button there. And it covers the middle part of Middle Tennessee down into northwest Alabama. And at the bottom there, they put the likelihoods of each threat that they're expecting below the little label there. So their threat for tornadoes in the watch area is high. Their threat for EF2 or higher or stronger tornadoes is moderate. Severe wind potential is moderate. And severe hail threat is also moderate. So pretty high parameters there for severe weather across that tornado watch. All right, and there's the text of tornado watch. We don't need to read that right now. I'll skip ahead here. All right, so here, remember they mentioned those storms are in West Tennessee and they're moving towards us. So let's look at the radar here as these storms kind of move in. So this is at 6:51 p.m. and right here in the middle of the screen is Wayne County, Tennessee. So remember I mentioned Wayne County is pretty much the furthest away from the radar here in Nashville that we can get. So the radar beam is looking really high up above the ground there in Wayne County. It's about 9,000 feet up. So we're not seeing what's going on near the ground. We're seeing about 2 miles above the ground. But we've got the radar reflectivity here at the top left. In the top right, we can see there's these greens and blues here right next to an area of reds. So green and blues are winds blowing towards the radar, and reds are winds blowing away from the radar. So right here, where these greens and blues meet the reds, that's an area of pretty strong rotation there, southeast of Savannah, moving into Wayne County. And then at the bottom left, this is our CC product, so the correlation coefficient, and it's pretty noisy. We can't really tell much from that. And then the bottom right, that's our spectrum width. We're not going to talk about that right now. So let's move ahead 5 minutes. That storm has moved into Wayne County. It's not a really huge storm, but it does have a kind of what we could consider maybe a hook echo there at the bottom left, but it's not really very well defined. It's kind of a small looking storm, but you can see on the velocity here, we still got those really bright greens and blues right next to those reds. So there's still pretty good rotation going on as the storm is moving into Wayne County. And we're looking at the bottom left here on the CC product. It's still pretty noisy, so we can't really tell much from that. So let's move ahead another 5 minutes. That storm has moved further into Wayne County. It's getting closer to Waynesboro there. And looking at the top right, you can see there's still those really bright greens and blues right next to those reds. So there's still pretty strong rotation going on there southwest of Waynesboro. But let's look at the bottom left at the CC product. Suddenly we can now see this kind of this rectangular area here of some really dark, deep blues. And that's CC as low as 20% or 0.2 that the radar is detecting. And remember that the radar beam at that level is roughly about 9,000 to 10,000 feet above the ground. So the radar is detecting very low CC right where there is very strong rotation going on in the southwest part of this storm. So the radar is detecting debris that's been picked up from an apparent tornado that had to have touched down somewhere here in southwest Wayne County. And that debris has been lofted up to the radar beam height. So it's been lofted almost 2 miles up into the atmosphere. So we probably got a pretty strong tornado going on, or has touched down before this radar scan there in southwest Wayne County. So let's move ahead another 5 minutes. Can still see that storm here south of Waynesboro. It's kind of taking on more of a hook shape now. We can even see that a little bit there just south of where it says Wayne on the image. And then there's still pretty strong rotation going on there south of Waynesboro. And look at the CC product. There's an even bigger area now of those dark blues or that really low CC. So we're seeing an expanding area of apparent tornado debris in the atmosphere at about that 9,000 to 10,000 foot level. So there's probably a tornado in progress going on there south of Waynesboro, and it's lofting a lot of tornado debris in the atmosphere. So if you were a NWS forecaster on radar, you could put into your tornado warning at this time, this is a confirmed tornado based on radar, likely damaging tornado going on there south of Waynesboro. So the storm continues there. Now it's southeast of Waynesboro. You can see the hook even better now there at 7:12 p.m. The rotation's still pretty strong there at the top right, just southeast of Waynesboro. Excuse me. And the CC is not as strong as it was. They're not as deep. There's not as much deep blues there, but it's still there southeast of Waynesboro. And I also want to mention there's another storm there in far southwest Wayne County that also has some rotation, and it's also got area there of low CC with those dark blues. So looks like we have another tornado in progress also there in far southwest Wayne County. But I really want to focus on this storm right by Waynesboro. All right. So I'm going to go back one screen again. So let me go through this progression of the radar again. Really just focus on the storm by Waynesboro. So here we're not seeing any tornado debris southwest of Waynesboro until we get to about 7:01. You see that explosion there of the really dark blues, and that kind of expands in area as it moves towards Waynesboro, and then kind of gets a little less there as it gets just southeast of town. All right. So what all happened on that day? Well, here's a map of all the storm reports that the Storm Prediction Center received. Blue dots indicate wind damage, green dots indicate large hail, and red dots indicate tornadoes. So you see there's a lot of tornado reports there in northern Mississippi. up into Middle Tennessee, but there's also some up in Illinois, Indiana, and looks like Ohio and northern Kentucky, and a lot of wind damage up there in Kentucky into Illinois and Indiana. Not a lot of large hail, but there's a few reports there in eastern Arkansas, western Tennessee, up into Illinois. So that really, if you remember back to those, the tornado threat level and the wind damage threat level and the hail threat level, that matched up really well to where they had all those threat levels. They had the damaging winds kind of to the north, the tornado threat a little further south, and then there wasn't a big, large hail threat. So they did pretty well as far as the outlook for this day. And this was back on December 23rd, 2015. And here in Middle Tennessee, that tornado we were looking at on radar was this EF3 long track tornado that tracked for 50 miles from the Lutz area of southwest Wayne County, just southeast of Waynesboro, and then passed northwest of Lawrenceburg and Lawrence County and ended southwest of Columbia in Murray County, Tennessee. So that was a major tornado there down by Waynesboro that we were looking at on the radar. And I mentioned that other storm in far southwest Wayne County. There was actually an EF2 tornado with that storm that moved out of Alabama and weakened as it moved into Wayne County, but it still produced EF1 damage with that tornado debris signature we were looking at. There was also an EF2 tornado. I didn't show that on the radar, but that it occurred a little earlier up in Perry County, up into Hickman County, and unfortunately that tornado killed 2 people in Perry County. And then we had another EF2 tornado way over here in DeKalb and Smith counties east of Nashville. So basically, all that instability we were looking at moving towards our area combined with that really strong wind shear that was already in place across Middle Tennessee. And we got, the result was a lot of damaging long track tornadoes there, especially in the southwest part of Middle Tennessee. And that's some of the damage pictures from that event. So if you get lots of instability combined with lots of wind shear, and you've got that source of lift, in this case, we had that cold front and that low pressure system across Kansas that was moving towards us, all that kind of combined to produce that severe weather across Middle Tennessee on December 23rd, 2015. All right, so what are some resources that you can look at as far as learning more about severe storms or more about what we talked about in this talk? Well, you can go to our website, which is weather.gov/Nashville. There's also the Storm Prediction Center site, which is www.spc.noaa.gov. And I'd answered a question earlier, if there's other courses you can take about severe weather. Google the COMET website, which is COMET, and that's basically a weather learning site, and there's lots of classes you can take on there if you want to learn more about not only severe weather, but any kind of meteorology, from winter weather to rain to pretty much anything is on that site, so you can Google that. And I'm trying to think of other websites out there. There's lots of weather resources out there. Google is your friend. If you ever want to learn more, just Google it and you can probably find some really good stuff out there. All right, so kind of wrapping it up here, you all have completed an advanced storm spotter course now, so you can print out your own certificate at home. I've got the link there on the screen, so you're probably going to want to write that down. And what it's going to do is it's a PDF file of this certificate, and you can print out the certificate in the PDF file, excuse me. You can put your name in the PDF file and then print it out, and that's considered an official advanced spotter certificate, excuse me, of this course. The date is actually correct. I know on the screen it says fall of 2016, but it's correct when you go to the link. So hopefully that all works for everybody. I'll leave that up on the screen so you can write that down and go print out your certificate. I know I covered a whole lot of different topics in this course tonight, and some of it may have been a little confusing. So if there's anything you have a question about, I'm going to stay on the webinar for about 5 more minutes. So feel free to, to ask me some questions in the chat. I'll also email you a link where you can download the slides so you can view those at home. And I'm going to type into chat here my email address, which is sam.schamberger@noaa.gov. And if you have any questions about anything, feel free to send me an email and I will respond to you when I can. So I hope you all enjoyed the class and you learned something new. And if you have any questions, feel free to type them in chat or send me an email. Otherwise, we're done for tonight, and I hope you have a great rest of your week.